Okay, given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So if we look at this tree, we can see the root node here is a 3, right? Okay, and then the root node has children nodes. So that's going to be depth of 2, right? The depth of the root node is 1. The depth of null pointer is 0, et cetera, right? So root node, depth 1, root node's children, depth 2, root node's children, depth 3. What is the maximum depth of the tree, right? If you search all the way down all of the paths to all of the leaf nodes, right? We can see for this tree, it's going to be 3 because these leaf nodes have depth 3. So pretty straightforward problem statement. We can solve this both recursively and iteratively. So let's look at the recursive solution. So for our recursive algorithm, basically what we're going to say at every node, we're going to first check, are we at a null pointer? A null pointer has a depth of 0. That is going to be the seed of our algorithm. It's also going to handle the edge case where potentially we have no nodes in our tree and we just have to return 0 because the depth of a null pointer is 0, right? So aside from that, that's going to be the first thing we do. The second thing we do have a node here when we're at the root node in this particular case, this example. So we're going to take the maximum of the depth of the left subtree plus 1, or whatever's greater, that or the right subtree, depth of the right subtree plus 1. Okay, we're going to do that. That's like a recursive call. So basically, what does that mean? What would that look like? Well, it's going to be like a depth first search. So in order to get the determine, okay, is this subtree have a greater depth, or does this subtree have a greater depth? In order to determine that, we're going to have to do a depth first search, meaning we go down then to this node and we ask the same question, but we don't know the answer even for this node yet, right? So we're starting to build a recursive call stack. So we'll go down this way. Okay, is this subtree have greater depth, or does this one? Well, we don't know. We have to keep going down as far left as we can go. Okay, we're going to keep going all the way down until we get to these null pointers here. So the depth of the null pointer is going to be 0. So we're going to return 0. And we're going to take the greater of these two subtrees plus, this subtree, depth of this subtree plus 1, depth of this subtree plus 1, right? So it's going to be 1, right? That's going to be, they're the same depth, right? So it's going to be 1 here. That's going to be the depth of this tree. So as far as, this point of the recursive call stack goes, like this thing is only going to know that its depth is 1, right? And it's going to start backtracking, right? And when I say backtracking, it basically the depth of this tree here is going to be 1, and it's greater than the depth of this tree, which is 0. So but really the comparison is this subtree's depth plus 1, right? And this subtree's depth plus 1. So it would be like 2, what's greater, 2 or 1? Well, 2 is greater, so we backtrack with this 2, right? We go this way, we do the same sort of comparison on this subtree now, which is plus 1, which is 3, and then this subtree, which has a depth of 1, right? Plus 1 would be 2 over here. So we do the comparison for this 3 and the 2. Well, the 3 is actually bigger, and then this is our root node, so that's the answer. In terms of the time and the space complexity, the time complexity is just going to be big O of n, because we have to look at every single node once. So that's just going to scale linearly. And then the space complexity is also going to be big O of n, because our recursive call stack in the very worst case can have all n nodes in this tree in the call stack, right? imagine the tree is like asymmetrical, to the asymmetrically skewed to the left, right? On a depth first search, in that case, you would literally have all of the nodes in the recursive call stack, right? So that's why that's linear in space as well, and not just constant space, right? There is space in memory in the OS for the recursive call stack. So, so we're just gonna say, let's do that first condition. So if not root, right? So either if we're at a leaf node or if literally there's just no nodes in the tree they give us, right? This handles both cases. We'll say if not root, we can just return 0. Okay, so if there were nodes that it gave us, this like seeded, this is gonna basically be the end of our depth for search. It's gonna end our search and it's gonna seed the backtracking, right? To start counting back upwards to know what those depths are. So we would basically just return at every one of these points in the recursive call stack, we're going to return the max of the depth of the left subtree plus 1, whatever is greater. So the left subtree plus 1 or the right subtree plus 1. So to get the left subtree, we have to call max depth recursively on this node's left child, right? And then plus 1, okay? And then what's greater, that or the other subtree, right? So the right child plus 1. And then we add 1 because, you know, at every like layer of the recursive call stack, we're going back up a level, right? When we start returning this, starting like at the leaf, the node, really this is like the node under the leaf node, right? The null pointer. But anyways, yeah, this is the recursive solution, and forgot a semicolon. But yeah, we can also do this iteratively. So let's go over that really quick. So we'll just do like the same example, but we're basically going to we're going to use a stack and do like do a depth first search again, kind of really similar to how the recursive one works under the hood. It's like alternatively, you might be able to do this with a breadth first search and a queue. I'm actually not sure. Drop a comment below on if you can do this with a breadth first search with a queue. But I'm gonna do a depth first search with a stack for the iterative. So we're gonna have a stack, and the trick here is when we put nodes in the stack, we're going to it's actually going to be a stack of pairs. So we're going to keep track of the depth of the nodes, and that's how we're going to find the max depth, right? So we're going to keep track of the max depth that we've seen. At first it'll be 1. Okay, we'll pop that from the stack, we'll put its children. So we'll put the 3, we'll put the 5, and you know, we also put the depths. So let's put those depths, and then right, we'll check, right? Can we update the max depth? Max depth was 1 before, so max depth is 2 is greater, so max depth becomes 2. We can pop this, check the 3. We'd put the 3's children to the stack, so put the 7, its depth is going to be 3. How do we know what its depth is? Well, we can literally take the node that we were just at, whatever its parent depth is plus 1. And you know what it is because like you'll see when we write the code, you pop it from the stack, you'll have the depth of the parent handy. So yeah, anyways, max depth here is going to be 3 once again. So that is the answer. And the time and space complexity is going to be the same as the recursive. So it's the time is also linear, right? It's the same. And then it's also just a depth for search algorithmically. The space complexity is going to be the same, but instead of like the linear memory in the OS for the recursive call stack, it's the literal data structure stack, right? Which also scales linearly, right? In the worst case. So yeah, we can write that code as well. So it's going to be a stack of pairs that we need. So say stack of pairs of the first type, and the pair is going to be a pointer to a tree node. And then the second type is going to be an integer, just to keep track of the depth. We'll say node stack. And then we just need an integer variable to keep track of the max depth that we've seen, right? It can start at 0. And then to seed the depth first search, we do need to put the first node in the stack. So we'll say node stack.push. We'll say root, right? Root is potentially null. So we'll handle that gracefully inside of the for loop. Root's depth is going to be, if root does exist, its depth is going to be 1. But we will definitely check if it exists before trying to push its children or trying to update the max depth, right? So if root is null, we don't want to update the max depth at all, right? Because that would be incorrect. So anyways, yeah, we're going to say we're going to say while the node stack is not empty. So not if, but this is like a loop. So while the node stack is not empty, while there's still elements, we want to grab the pair off the top of the stack. So just say p short for pair is going to be equal to node stack dot top. And then we can pop from the node stack because we don't need that top element. That we have access to it now. So we can safely pop it. We don't need it in the stack. If the node doesn't exist, then it's like a no op. We don't want to update the max depth, and we don't want to push its children because that's going to be a memory bug, like an error. It's a null pointer isn't going to have any children, right? So, and it also has a depth of 0, right? So we don't care about updating the max depth. So we're going to check if p.first before we do anything. Okay, and dot first is going to be the node, right? That's the first element of the pair. Second is going to be the depth of that node, right? So anyways, yeah. So if the node exists, we want to try to update the max depth. So we'll say max depth equals the max of whatever the old max depth was, or p dot second, right? So the depth of that node in the stack. Right. So we just updated the max depth potentially, right? And then the next thing we want to do and the last thing we want to do is just push both of its children, right? And if its child is null, that's totally fine because we have already considered that what happens in that case, right? We're just going to push both of its children regardless of whether they are null, right? So we're going to say node stack dot push the p dot first. So that's the node. It's going to have a left child. And how do we know the depth of its children? Well, we just take the depth of this node plus 1, right? We can increment it like that. And then that's how we're going to find the max depth iteratively with a depth first search. So then we'll return at the end of this, we'll just return max depth, right? Okay, so that's pretty much it for the iterative. Hopefully this is helpful, and I'll see you guys in the next piece.